Welcome. In this lecture, which has multiple sessions, we'll explore support vector machines, or the SVM, with the kernel trick. The main concepts are that the kernel trick, which we saw in a previous lecture could be used to create an SVM, can also be used to score data. We'll score a data using the primal Lagrange equation. The kernel function is employed in the score as well as in the creation of the SVM. Support vectors are primarily used to compute the score, and these produce nonlinear separation, which we'll explore in a couple of examples. A problem that we would like to keep in mind is how can we evaluate a Gaussian kernel, for example, in an SVM classifier. Let's recall where we are so far. In part 1 of the kernel trick, what we did was we had a symmetric posi-definite kernel function, and that means that if we have finite dimensional data and a finite number of those data, that we can create, using this kernel function, we can create a gram matrix. And the gram matrix, we don't compute it from the design matrix, we compute it in place of the design matrix. And the SVM dual objective then becomes this. There are extra terms, but this is the key part, is that in the original SVM, we would have had to compute these matrices, and if the kernel is, for example, a Gaussian kernel, these could be infinite dimension. But computing this gram matrix, it's a square matrix with the numbers and rows of columns equal to the number of data vectors that were provided. And then we can compute the Lagrange multipliers using sequential minimal optimization, an interior point method, or whatever method our SVM computer will provide us.